Hey everybody, so I want to start off this video by talking about Miriam Mirzakhani because uh, without her, none of this would exist. And I think that if she was alive today, then uh, this would be coming from her rather than from me, like an idiot. Uh, but yeah, so I just want to start off this with that overall and that acknowledgement, right? Like, not like the entire basis of all of this is like her research, right? Her research specifically into mathematics, moduli spaces, for me, hyperbolic geometry, ergodic theory, and symplectic geometry specifically. Like that's what she won the Fields Medal for, right? Um, I'm positive that she would have gone over this stuff and pointed it out to you like years ago instead of me. But so here we are in the world today. But so the first place that I want to start off with within this is going over some of the like theoretical background behind this, right? Because and proving to you the theoretical background behind this, because what I'm going to showcase to you in this video is pure theory at this point, right? There's no one that has proven it out definitively, and then so I mean I have pretty definitive proof here. So that's essentially what I'm going to showcase to you within this. And the very first place that I want to start is this. It's called K-furthest neighbors. I've gone over this before. My channel was probably about like the third of the size that it is today when I invented this overall. But just as a general overview, I created this very simplistically and very like firstly as a joke, right? Like as a just playing around one day, like I was bored, and then I had the concept that K nearest neighbors is like one of the biggest algorithms that exists within AI overall, right? And then so I mean specifically what it does, it's K nearest neighbors, right? It calculates the nearest relationship and the nearest distance between like two latent space points, right? And then cool. So within that, wouldn't it be cool then to have like the furthest neighbor as an anchor, as a like an anchor point? So if you have like the nearest neighbor, and then like the complement to that to me would be the furthest neighbor, right? And then if you play around within that, then you'd be able to measure and predict everything within that, right? And then so that's step one within this. Step two within this is going back to this, right? That very specifically. That there's within these latent spaces, there's a geometry that exists, and then that geometry is has physics characteristics, etc. Right? It's a latent space is created, a geometric structure is created. And I mean that's all here, right? And then so the models, like for example, like gradient descent, etc. The reason why they work overall to me is because they're essentially measuring the shapes of these objects, right? Like the shape of a data set within the latent space overall, very specifically. And then so if that's true, right, if that's accurate, like if you can do that, then I should be able to prove that out, right? Like I've always been kind of against the academic model overall because to me it's backwards, right? Does it work in theory as opposed to does it work in practice? To me, if it works in practice, then it proves the theory, right? And then so within this, we have these concepts overall. So first of all, we have going back here, K furthest neighbors and K nearest neighbors, right? And then so within this particular notebook here, the thing that I want to showcase to you is this very last cell. And this is why I knew all of these experiments with regards towards topology capsules were going to work, because I have this experiment in my back pocket from probably about like a year ago or so ago now, right? And then so this is the K nearest neighbors and the K furthest neighbors, and then this is utilizing fashion MNIST, right? So essentially I'm utilizing K nearest neighbors and then K furthest neighbors to define and understand the actual topology of the latent space in this specific instance of the fashion MNIST dataset, right? The geometry of the fashion MNIST dataset as an AI model understands it. And then how do I know that that's accurate? Because I can do things like this, right? Reconstructing the dataset utilizing literally only the shape. So then I essentially take this shape, right? And then, okay, if this is accurate, let's strip out everything that's related to the actual data set itself and then let's get the model to predict the data set based off of this. And then if you, this model the X's are where it's hitting the accuracy, right? X's over blues, and you can see 100% accuracy, literally. The greens are where it's adding additional data set, like missing components of the data set. Like I can't overstate that enough, right? And then so I've sat on this for a while and I've known this, but then so like what exactly and how exactly do I turn this into something? And then so today I've been experimenting around. And then I've created the very first step is like this is I'll leave you this all three of these collab notebooks, right? So this very first one, K-furthest neighbors, this is a very integral part of this entire process, which I'll explain here. This second notebook here, what we're looking at is my very first attempt to essentially prove out this concept more than just what you're looking at here, right? And then so within this, I'm utilizing fashion MNIST as the data set here, and then we're utilizing it's zero training loops, CPU friendly, full topology driven. So this notebook builds a topology capsule, a compact graph-based representation of a data set's latent space using only pairwise structure. So it's utilizing, in this instance, so KNN is an attractor, right? And then KFN is the repulsor in this instance. So rather than utilizing it to measure the entirety of the latent space itself, utilizing it to arrange and then create boundaries within the latent space. So after the capsule is built, the raw pixels and embeddings are discarded. So like any sort of thing that's related to the actual data set itself, any labels, etc., are all just thrown out. The model doesn't utilize any labels up front, right? All label inference and downstream evaluation are performed solely from this fixed capsule. So the capsule itself is training on zero labels. That's the most important thing within this concept to understand and to highlight within this, right? So utilizing fashion MNIST as the data set, what I'm doing is I'm taking the data set itself, and then I'm taking these two calculations, K nearest neighbors and then K furthest neighbors, and then I'm utilizing those to create the shape of the data set, no gradients, no backpropagation, etc., just purely the shape. So this is a graph-based model, essentially, literally, right? I'm taking and making that shape into a graph, and then literally the model is just reading the graph and the shape, and the shape of the graph. Then when you're testing the model, you're testing it against the labels, right? That's the only time where the labels actually come into play within this particular model. And then so it's testing against the fashion MNIST labels, but again, the model is only trained on the shape itself. The model is not touching the data set. Like fashion MNIST as a data set does not exist to this model. Only the shape of fashion MNIST exists to this model. So the core idea is instead of training a model to memorize labeled examples, we capture the data set's intrinsic geometry. In this view, the data set is equivalently defined by its near and far relationships. Again, I'm utilizing KNN and KFN. I want to recognize this upfront, right? Like, so K for this name, I made this, and I can't stress this enough, right? I made this as a joke initially. Like, we trained them wrong on purpose, right? That was the whole entire idea. This ended up working overall within this. I think that there are far better calculations that you can use and you could couple. I'm assuming that you leave these two in, but there's definitively better ways to go about this overall, and I want to highlight that, right? So essentially what this notebook that we're looking at here builds, one, it's a compact embedding for distances. We're utilizing a slice of the fashion MNIST data set to keep it really fast, right? These topology capsules are loading in like 45 seconds and they're not training. And that's another, probably the second thing to highlight within this is that this is all running on CPU, taking 45 seconds total, 45 seconds to 2 minutes per every single model here that I'm going to show you. And then that includes creating the graph and then essentially aligning the model based off of the shape that's created, right? And then so here's kind of like I'll go deeper, and I'll give you a document as well that goes very deep into the actual, like what's going on behind the scenes here. If you're like very curious as to that, I'm going to give you all of the resources that you would want to dive deep into this. And then so here we go. Basically, I'm going to show you these test results first of all. So these are just, again, my tests showcasing to you overall that you can actually do this. So this is with my very first test within this, and then I'm getting essentially like I'm testing and I'm trying to see if there's an improvement between k nearest neighbors, and then utilizing KNN plus KFN, and then in these initial like benchmarks, I can see like and it's basically like a pretty insignificant of a difference, right? 0.766 compared to 0.769. That number is better, but it's statistically the same overall. But what matters to me is that okay, 76.6% accuracy. That's pretty good, right? Like again, it's training off of zero labels, right? It's just like off of the shape, and then it's getting 76% accuracy. And then so up front, again, if this shape, if this topology, if this geometry did not exist in the ways that we're talking about or looking at within these things from a physics perspective, then you literally wouldn't be able to get 76% accuracy by just training on this shape that exists, right? It would just be pure voodoo, and you'd get 9% accuracy, coin flip accuracy, right? But that's not what happens here. And then so going through here, just so I want to essentially understand and test out this shape better, right? So then what I'm doing here within this particular test is measuring like deviation and then trying to understand exactly what is going on within this. So measuring unlabeled accuracy versus the like internal model test accuracy, right? And then so we can see internal model test accuracy without like measuring off of the shape is what we would expect, coin flip accuracy, because there's nothing there, right? But then what we can see here, 74% accuracy by training on the shape. So it wouldn't jump from 12% accuracy to 74% accuracy if it were training on nothing. If this was all, again, made up fiction, if this weren't actually doing anything, then how do you account for like a jump from 12% to 74%? Again, like, and the only thing that it's doing is training off of the underlying shape of the data set, essentially. And then so going through here, let's run through a few more tests and then, just illustrate that out. And then so here at this point, I start trying to increase that accuracy overall, right? And then so trying to turn the dial, and then looking at and trying to understand if I can measure the geometry better is basically what I'm trying to do within this test. And I get more readings of the geometry, but I'm not able to increase it above that 76.7. And then so next test I go through. And in this test I had a lot of I had this is a soft error that ran through every single time, right? And then so you could clean this up, but it's just a soft error that ran. Again, I'm just doing my internal testing within this, right? So I didn't really care about the soft error. But so what I'm doing within this test is I'm increasing the budget and I'm increasing the noise within these tests, and then I'm testing it versus the capsule versus the linear probe, right? Which the linear probe is just testing essentially the baseline model. The capsule is testing essentially the model learning and utilizing that latent shape in order to make its predictions and its determinations, and then we're shooting noise into that as well, right? And then seeing how robust these things are when we do that. And then so what we can see here with a low budget, we start increasing the noise, and then our accuracy starts to go down on both, which is expected, right? And then so this is all expected. Accuracy is going down. Accuracy is going down more so on our capsule, but it has more to lose, right? And then so let's increase the budget. Increasing the budget automatically jumps the power of our capsule very dramatically, right? So our capsule with zero noise is scoring very high. And then all of a sudden with that increased power, what we can see is that the noise is less robust. It's able to not penetrate there, and then it gets lower here at 20% noise. And then it starts to, so at 20% noise and a power budget of 50, it's starting to go down, and then it goes down very significantly from there, right? And then we give it a power budget of 100, and then we injecting 10% noise. There's a 1% decrease. 20% noise, we get 4% decrease here, right? So it started it's starting to impact less. And then at 40% noise here, we get 56%. And then we end up at 60% noise, and then we still end up at 42% accuracy. And then we increase the budget to 200, so make the model even more robust. And then it's all of a sudden we're getting 73% accuracy with zero noise, 71% accuracy at 10%. And then it drops down at 60% to 49, but at 50%, at 40%, it's still at 61, right? So it's like it's the more budget that we're giving it, the more robust to noise overall it becomes. Whereas the linear probe is just the same overall, right? And then so we increase the budget to the kind of max to 400, and then we get 74%, 74.4% as our baseline, as 74.7% as our baseline, 74.4% with 10% noise, 72.6% with 20% noise, and then at 40% noise in this case, we end up at 66%, and then we get a 12% decrease at 60% noise down to 54%, but still at 54%, 60% noise, right? The model, so it's A, the shape exists, B, the shape is very robust and easy to measure and pick apart, at least with the fashion MNIST that we're looking at within this particular testing, which is very important overall within this, and I want to highlight that right as we come over here to the actual notebook that I want to demonstrate for you here, which is Topology Capsules V1.0. So an overview, this notebook introduces Topology Capsules, a graph-based framework for learning and inference without deep training loops. Instead of relying on backpropagation, the methods build topological capsules, compact spectral structures extracted from graphs of data, and uses them for semi-supervised label propagation and transfer. The core idea: rather than treating similarity and dissimilarity symmetrically, topology capsules explicitly model both positive affinities, who is close, and negative repulsions, who is far, and reconcile them through signed graph Laplacians. This gives a capsule-like latent space that can be probed with very few labels. Here's kind of just like all of the key features here. Again, I'll leave you a doc here as well if you want to get deep into the actual architecture. Here's all of the benchmarks that I did within this. So overall, the three benchmarks that I'm including within this are Fashion MNIST, SciFar 10, and then I'm utilizing, and then this is like a subset of SciFar 10, very specifically cats and dogs, right? And then so cats versus dogs, very specifically, and then so. Overall, topology capsules bridge geometric learning and the graph signal processing. They sidestep costly neural training. They expose both attractive and repulsive structure in the data. They work in low label settings, making them ideal for semi-supervised problems, and their interpretable capsules are frozen spectral bases with clear diagnostics. So in short, topology capsules explore how to capture the shape of data through graphs and use that to shape directly for learning robust, interpretable, and lightweight. Again, this is essentially like the power of a toaster overall, and then within that, and zero training on this, right? That's the other thing, is that like I'm not utilizing any sort of classifiers. I'm not utilizing anything that is inherent to what we would call or define as like classical AI, right? Like absolutely nothing at all within this, and then including like again backpropagation, gradient descent, all of those concepts, like anything that's related to deep learning, right? This would be a model that exists completely outside of deep learning, although it's important to highlight and point out that like the next use case and what this could be spread into and brought into very easily would be modifying all of this for transformers overall, right? And then so if you're interested in that type of stuff, I could 100% do it for you. I'm not going to. So this is all MIT licensed. Everything that I'm showcasing here on this video today is MIT licensed overall. And I'll leave that there. And then so let's go ahead and go through the notebook here. And then so again, here's all of the code and that we're looking at here. And then so you can see the first test was on SciFar 10. My very first test that I skipped up from was Fashion MNIST, but I showed you all the Fashion MNIST tests plus these new ones here within the model. I was able to get it up to, I think it was like 80% accuracy on Fashion MNIST, around there, 78%. And then with SciFar 10, I start running into issues, right? And then so when I'm building out these topology capsules, the very first question I have in my mind is like, would it be possible to build kind of a universal topology capsule, if you will? And then by doing this SciFar 10 testing, I was very specifically and easily able to determine very quickly, no, right? Each one of these capsules needs to be very unique to the data set, because essentially, so how I look at this overall is how this is working is, again, and why this is working is very specifically because of the geometric structures that are in existence when it comes to these data sets, and then the emergent geometric structures, and then those emergent geometric structures are actually what the model's learning on, right? It's not it maybe learn, and it learns to start to bend that towards the like human labels, etc. But that's what I am specifically trying to avoid within these topology capsules, right? So essentially, what happens within each one of these topology capsules, very specifically, is that it creates the latent space, as I talked about, right? The KFN and the KNN, and then we understand exactly how that works. You can see here that you take the features of the data set, right? So in this instance, CIFAR 10, it takes about 14 seconds just to extract the features, right? And so think of the features as like, these are the features as defined by like the characteristics, geometric characteristics of the data set that I want to define. And then I build a graph based off of that. So that like in total, you're looking about 25 seconds for that entire process, right? For the CIFAR 10 data set. And then from there, it's just a matter of reading the graph, right? And then when I read that graph, my very first test on fashion MNIST here, or on CIFAR 10 here, as you can see, like much lower accuracy, like 36% accuracy, but that's a lot better than coin flip accuracy. CIFAR 10, if you like, is a hard data set for models overall because it has a lot of blending characteristics. The images are very small, and then you have categories like cats versus dogs, where like some look the same overall. There's not like and then you have like multitudes of breeds of dogs, right? And then dogs can be big or small. And then same thing with like there's vehicles, and then so like a truck versus a car versus like a tank versus, like just different, these things are just harder overall for the model. So like to me, I consider like fashion MNIST like kind of like preschool for the model, and then when we get into like a CIFAR 10, that's kind of like a more real test, right? And so from here, I'm trying to refine and build out a specific topology capsule for CIFAR 10. I'm happy enough with that, like 78% or whatever it is on the topology capsule for the fashion MNIST, but I want to see, okay, if all of this works out, I should be able to adjust and dial this same exact dial for this CIFAR 10 data set, right? Oh, and then so that's very specifically what I do somewhere here. And then so my very first test within this, I test it out, and then I get it up to 41% accuracy, so higher than the first test, right? And then so what I want to do from there then is understand exactly how this. So I take the example that I use as cat versus dogs, right? So those are actual data set parts of the CIFAR 10 data set. So then I narrowed down specifically to this data set, right? Okay, let's essentially create all of the knobs that I need in order to best interpret cat versus dog within this, right? And then I'm just going to focus on cat versus dog. And then so that's what I do for the testing here. And then when I do that, essentially what we can see is same thing, right? So the data set loads the data set, it's almost instantaneously. So then I have, it's 4,000 examples. I have 1,998 of cat, 2,002 of dog. And then from there, it takes the raw features, right? And then so in this instance, I start learning, I'm tweaking the dials of the features, right? So this has more features than it did before with the CIFAR 10 alone. And then what I do within that is I essentially create 3 individual topology capsules per each one of these features. So each one of these individual features becomes an individual topology capsule. And then I take the 3 topology capsules and then I blend them together. And then we get the final topology capsule, which gets us up to 60% accuracy on this cat and the cat dog data set specifically. But when I very first took cat dog, it was scoring the same as the CIFAR 10, right? Like in like the 40% range. And then so getting it and increasing it from the 40% range to 60%, very significant, right? And then again, the big thing to note within this is that it's not utilizing these labels, right? It's utilizing the shape of these 1998 examples of cat versus the shape of these 2002 examples of dog, and then utilizing that shape essentially to navigate this overall. And last thing I'll leave you with here around all of this, giving you everything that you would need open source here, is the as essentially a doc. This is a general overview explainer and then the technical overview as well. So Topology Capsules general overview. So you can read through the full document here. Again, if you're more interested in the the specifics, this top portion is very specifically for just like a general overview. And then if you want to dive deeper into the technical specifics, again, I give it to you all through here as well, right? But then here's even more, and you can see, and then just kind of just a recap of all of the benchmark tests that were done overall, and essentially everything that you would need in order to reconstruct this, what we're looking at here, and to prove out this concept overall. So this concept is topology capsules. I think topology capsules are pretty cool, pretty awesome overall. The geometry is pretty cool, and again, none of this would exist if not for Miriam. So that's where I'll start and end this video. And if you like this type of content, please like and subscribe. Thank you very much.